My name is Cassidy Mentus, and I'm presenting on applications of compressed sensing to detecting low prevalence disease. So the original goal I had in mind with this started out in April when there was very low testing capacity for COVID-19. Since then, it's moved on. And, in July and June, it was more about quick turnaround. So to increase capacity and turnaround, you could pool tests together. And if there's low prevalence, then you know that a test with many people's samples in it will come out negative, and you're going to gain a lot of results very quickly this way. But this is sort of an older way of doing things. And even compressed sensing has been around for a while, but I would like to shorten this process and make it one step by decoding all of the results after the pooled test, because usually you would have to do another test to confirm that each person has a result. So I'm going to introduce some new ways of doing that, and also with a perspective on modern assays. So I sort of described that in this slide, but I'm going to describe the two-stage group testing, applying this sensing and decoding technique, which is from compressed sensing under a Poisson noise. I'm going to give you some new techniques for decoding the group tests. I'm going to show you how to apply them with different modern assays, such as digital PCR or neural network-based assays, and also demonstrate the efficacy of these tests that they could be carried out by lab personnel or liquid handling machines. All right, so this is basic group testing. So suppose you have 15 people. The easiest idea to wrap our heads around is if we split it up into these partitioned groups, no overlaps. If 2 come out negative, then we already get 10 tests done. We didn't have to do those 10 tests. And so here we'd have to do 3 tests, and then the positive one, we'd have to test everyone. So that would make 8 tests. Okay, so, but one of the ideas here is that there's a screening round, right? So you could tell everybody that they're negative, and you could get your workforce, your football team, or whatever ready to go for the latter half of the day if you reported it with an app. So this is just like a hypothetical testing plan. You could collect samples, very self-administered collection like saliva, you can spit in it, transport it to the lab, do a group test, get back most of everybody you need and send it via, electronically. However, you could identify the people with their test using like a barcode, QR code. And then in the latter half, you could test a positive sample. But I'm sort of interested in getting rid of this bottom, let's see. Yeah, getting rid of this bottom part right here. I don't want to do that second stage. So let me just elaborate a little bit more on group tests. It's not all about splitting it up into even non-overlapping parts. Sometimes it's better to have the parts overlap, because when they overlap, you're going to get sort of like this bitwise operator looking thing where you're going to eliminate a lot more people after that first round, especially in the much lower prevalence region, like lower than 2%. And you're going to release, up to 96% of people to go and work while using, a fifth of the tests. And then the other people you can hold back. But we can do a lot better than this. So let's talk about compressed sensing. I do have to say that it's not only to get, just move this pointer out. It's not only to get perfect results, but sometimes you just want to increase the confidence about who you're releasing back into the workforce. You want to release those that if you say they're negative, then the worst case is they have a very low viral load. And, we have to have some kind of fault tolerance, because we do have to do something about the economy. But this isn't really only about COVID. It's about any test. It could even be cancer genomes and stuff. So, all right. So you want to mix the samples into pools. You want to test them. Where you're going to get back is you're going to get back a noisy measurement of the virus in the pools. It's not just true or false. It tells you an approximate idea of how much virus is in each pool. And then you bring it into a algorithm, and the output is going to be who has it. So it's going to be both the plus or minus, and it's going to be the viral loads approximately in each sample. So you also have to input a model. So we can describe that a little bit later. So I can just show you some results. So on the left here, what's important to look at is that we have 1,000 people that we're testing, right? So that's like right here, 1,000 people. And basically, this is the group testing scenario. One stage you do 160, in total they need 245. So that means 80 people out of 1,000, keep in mind, had to be held out. And that's pretty good, but we can eliminate a lot of this, maybe at the cost of some false negatives that are on a lower viral load. And here they have, this is Ghosh and Gopal Krishnan are another group that from IIT who apply a similar, or also apply this technique. They're really the first people to have a paper out on this with regards to COVID, but I've also been working on this independently, and I use a different model for noise. So they also show that you can use one round, 93 tests. If there's less than 1% prevalence, you can get 961 people, their results. Okay, so I'm just going to zoom through because I have more slides than there's time. All right, so PCR is the usual way we do this. The typical PCR, what it does is every cycle it multiplies the virus that's in the sample. And if there's more virus, it's gonna reach the threshold faster. And that'll tell you the concentration. Digital PCR splits up one sample into 20,000 micro tests, basically. And the number is gonna be a Poisson distribution. At the end of the day, this is also based on a Poisson distribution because it depends on how many viruses are getting into, or how many strands of RNA are getting into your sample. So that's why that justifies the noise that I use. And then we have this neural assay, which is completely new and completely clever. Unfortunately, I didn't put the name on the slide, but you can look this up. It's from Oxford. I think Nicole is the anchor author. So yeah, all you're doing is taking a picture of a microscope image, and then you're using like a image identification. It just literally counts how much virus particles, and you can do more than one virus at once. So this also is another, here we have a Poisson distribution because you're counting dots in this area, right? So here's a mathematical model. So let's just look at this. Let's just go back here for a second. So here, basically, for each pool, you're taking the average of all the viral concentrations of people who are going in here. That's a linear function. And it just turns out that it's a matrix multiplication where you're taking the average of everybody who's in a pool and you're assigning that to viral concentration. But that's like an underlying model, right? It's sort of a hidden model. And the measurement is really what you see is this Poisson. Phi is our matrix, Poisson phi times x. So let me just go over these variables real quick. X is going to be everybody's viral concentration. The white blocks represent that they don't have it. So you can see it's a very sparse regime here. When you multiply it by this matrix, it's going to confound things a little bit, but the pooling matrix is designed in such a way, phi, the pooling matrix, such that you can basically decode, it's almost an isomorphism on this very sparse class. And so basically, if the matrix is approximately a random sparse matrix, then it will give you exact decoding on sparse vectors. And if you add noise, then this slide conveniently ties right into that. So here we have sparse samples. The big breakthrough of compressed sensing is that if K is the number of samples, then you need approximately K log N or K log N over K measurements, which is much smaller than the number of samples, right? Because yeah, so well, it's big O. So there's going to be a multiplicative constant here. But as it grows, you can see that this will be a lot smaller. So yeah, or K log K maybe. It depends on, yeah, so if the prevalence is low, this is going to be a lot smaller number of measurements. Anyway, so the way you're going to be measuring, the way you're going to be predicting who has it is you're going to do a maximum likelihood estimate with a sparse penalty. So one sparse penalty is if we just use a lasso, we use an L1 norm. And why does that work? Well, let's just review that. So this is the L1 ball, right? So usually the ball is x squared plus y squared, et cetera, is equal to 1, and that will give you a convex shape that's round. But when it has these points, you're probably going to, your contour is probably going to land on the point. So therefore it's going to detect a lot of zero elements. And but this isn't rigorous so far. It's just, a good idea, but it is in fact true. If you have good pooling designs, it does give you, there are accuracy guarantees. And this was discovered by Candace and Tao and Donahoe. And the work that I'm using is based off of Willett and Roginski and others. And so here's the pools. I can just go through this. So the pools have to be good expanders. Basically, that means that if you know sort of what the degree of the left is, then if your selections are sufficiently small, then basically there's the set that it's going to project onto is as big as the degree times this set. So if each guy projects onto about 2, then it's actually going to multiply it by 2 and 2 elements, and there's going to be very few collisions. So you can see already how that sort of spreads things out, but it guarantees this isometry. So basically, not only from this combinatorics point of view is it good, but also geometrically, it preserves the distance between different elements when they're sparse specifically. So, and incoherence is another thing that will also guarantee good recovery. So, yeah, so the optimization problem. So what I introduce here is I introduce using an entropy regularization for a Poisson variable. Another thing that I'm not the first one to introduce, but I think I give a new rationale as to why to choose this is a logarithm penalty. And then you can also try lasso and L2. So let's just look at how these look. Right, so so a penalty, the more you go to the right, so the larger your viral amount is, the more it penalizes it. But you want them to taper off, and you want them to pinch in at a cusp here. And so that's basically, as you optimize this, it's going to slide a lot of people off to 0, like it's slipping off a slope. And you could see the sharper penalties do a lot better than these just straight line L1 penalties because they shrink the loads too much. So let's look at the maximum likelihood estimate without any penalty. What you get here is, in the red, you get false positives. So on the x-axis, not sure if you can see, that's the true viral concentration. On the y, it's estimated. So if you're at 0 and you're estimating something positive, that's false positive. And if you're actually supposed to be positive, but you estimate a negative, then you're a false negative. So maximum likelihood estimate isn't too good. So let's start to penalize the entropy of our viral concentrations. All right, great. So that did a little bit better. You can see that these false positives are starting to go away at 10. Let's go to 20. The false positives basically just vanish there, but you can do a little bit better. And then at 30, it looks just right, except you introduced a false negative. But mind you that these are in the lower concentration area, so you can actually control for, not for, convalescent cases or not very strong cases. So, I mean, really, we want to get as much people as quickly as possible back into normal activity, right? It's not only about accuracy at this point, but it's not only about COVID, it's about all tests. So this is a broad way to test people for a low prevalence virus to prevent some kind of problem. And also you can reduce the risk for them personally as well. So let's look at what happens. This is like the regularization curve. So what happens to the predictions as we bring alpha. And this is for the same data set, bring alpha to different values. You see here, the blue are the people who are actually negative. On the y-axis is their predicted amount. The red people are positive. Great thing is the red is all pretty stable. It's not really changing as you increase your penalty, but as you increase your penalty, those negative people are pretty much vanquished by 10 to 20. So that's why there are theoretical reasons for this. There are guarantees. You can see that it's working out perfectly by and large. So here's a new way to apply it. This is a thing called tensorized compressed sensing, where you basically are taking a tensor product of your matrices, but in planar language, what you're doing is you're pooling your samples. So on this side, like let's just look at this right here. That's the same thing as we were doing before. We were just pooling samples and testing them, right? Now what you can do is you can do that. Suppose you had 100 viruses you wanted to do, and you had a probe for each virus. So you could think of the viruses like they're people. You could sort of, like they are people. You could reverse your perspective, and now you have a pooling scheme for the viruses. So first you pool your people, but actually you copy it. You copy that pooling for the number of times you want to pool your viruses. And then after that, for each of the pools, you put in your selection of probes to detecting viruses. And if there's very low prevalence, so it's like you wanted to test, suppose you could test 1,000 people with 100 tests for one virus, or you could test one person for 1,000 viruses with, well, let's use smaller numbers. Okay, 100 people, 10 tests for one virus, 100 viruses on one person, you can use 10 tests, right? So now this is basically multiplying those two for 10,000. That would require 10,000 tests if you're doing 100 people for 100 viruses. So now, but the actual number of tests is 10 times 10, which is 100. So that's 100 times a decrease, but also the prevalence is going to be have to be a lot smaller, but it's still going to be useful. Maybe people are in a contact region to risky viruses and stuff. So this is basically a mathematical description. The important thing to look at is, like, we have two matrices here. Before we had a matrix V for samples. Now we have a matrix C for the number for the probes, or for DNA or what have you. It's going to be equivalent to, X isn't going to be a vector this time. It's going to be more of a matrix that you're going to list each person, but then you're also going to list the virus presence in each person on a different axis. And then you just do this multiplication that it's phi on one side and C transpose on the other side. So that's what it's equal to. So now let's switch topics a little bit. Okay, so I talked about uninformative priors as being a penalty before. Like most penalized optimization problems, you could look at them from a probabilistic point of view, right? We were looking at the negative log likelihood. So let's just flip the negative sign on that again. If we take the exponential of this, we get our, so this is conditional likelihood of your measurement given the actual true virus, right, amounts. When you do this, you get this times this factor right here, which can be interpreted as a prior distribution on X. So could we have an uninformative prior? So usually we think of Jeffreys priors, but there are things called reference priors, which are equal to Jeffreys priors in our case. They maximize the mutual information between the prediction and the distribution of what's actually going to be there. Really, they also maximize the predictive or the sway that the data has on your estimate. And logically, I think that's what we want, right? So, and I don't really see this discussed this much from this point of view, although there is some literature on this. So how can we do some, maybe going on to more rigorous math about this, but so what we could do is maybe I should go just to the second slide. So basically, when you matrix multiply, what you're doing is an equivalent model would be to split this up. So he's going to go into these groups, and she's going to go into those groups. So you split it up, and G is the group size. You make three Poisson random variables. And then you add them up, and you get your observations. So we can instead, so this is X, and the split up random variable Z. You have information there, which you then lose when you crunch them together with this, when you sum across the rows. So there's a data processing inequality, which tells you basically the information between the first and the last step is going to be less than or equal to less than or equal than the information between the first and this second split up step. Okay, so therefore we can find the uninformative prior for this. And it's essentially going to be as if we had a Poisson random variable in X. We saw that before I did Poisson entropy. So I had Poisson entropy, and it's like, why does that make sense? X isn't a Poisson random variable. Or yeah, where does it come into play? There it is right here when you split it up. So you want to maximize that information. So we can allow ourselves to look at uninformative priors then, which maximize the mutual information. So 1/2 log of X should be good. And that reminds us of the entropy penalty that I was using before, which basically, yeah, you're trying to find the least noisy solution, which will add up to give you the observation. And the entropy of a Poisson random variable, it turns out, is actually going to be big O of log of X as well. So there's some connection there. I have yet to optimize this because this doesn't have a, so this is 1 over square root of X, but even this log of X has a vertical asymptote here. So it doesn't come in and pinch to 0. So you're going to have to threshold as you're doing your optimization and maybe throw out viral concentrations and make them 0 as you go along. But I think that the penalty factor is already chosen for you because you're choosing the right prior. So there's something very theoretically nice about this. So one other application that I had in mind with this is that you could have still Boolean testing instead of, so this is quantitative testing, but there are a lot of tests which aren't at the level of sophistication of quantitative measurements. You could have Boolean testing or true false testing, positive or negative. And now you can say that what if X wasn't viral concentration, but you were looking at X is going to be the probability that X turns out positive. So it's not exactly the probability that they have it, but it's the probability that if you run them through, then X turns out positive. So you can use the same point of view and find the Jeffrey prior for that. And I didn't draw it, but maybe I could just draw it here. Yeah, so the Jeffrey prior for that will be like an arcsine distribution or a beta prior, right? Great. Okay. So it's kind of like this, where it tends to, so this is the probability that X is positive. And basically, it's going to go between 0 and 1. So as you optimize this, it's going to give you a more rigorous terrain. So that might be a problem because you don't have the numerical information. But trying different penalties, you might find that you do narrow it down with some trade-off between false positives and false negatives. That is really good for reducing risk and just getting as much people back into play in a certain situation, or just reducing the risk overall. That if you say we got a cheap test for you for some disease, then the chance that that we catch it is going to be very high. You can apply this method to it because it would reduce the cost and allow you to produce higher volumes, and you'd be able to offer that to more people. So it's been great presenting to you at DSAAI and Florida Atlantic University. I'm incredibly honored that I've been chosen to present my work, and I also hope that you really enjoyed it and that you learned something new today. And maybe this inspires you to come up with more mathematical work down this line, or computer science or machine learning work down this line. All right. Yeah. Thanks.